Yeah. So good morning all. Today we'll start with the actual concept of the embedded learning program, which is transformers. Okay. So far what did we discuss in the embedded learning program this semester? Where did we start and where did we come till? We have started with neural networks in the last semester, where we have covered two important neural networks, which were ANN and CNN, right? After that, how did we start this semester embedded learning program? We have started with RNN, right? What are RNNs? Recurrent neural networks. Why do we use RNN mostly for? When you have sequential data, we use RNNs. When you talk about sequential data, what type of data comes into picture? Mostly when I talk about sequential data, we deal with natural language processing. Okay, voice or text data. So there are so many AI applications that we use in our daily lives, in a real-time life, where we deal with natural language processing. For example, let's say text summarization, language translation, okay, and then chatbots. So many applications deal with text as input, and this text has to be processed, which is usually referred to as natural language processing. So the type of neural networks which deals with natural language processing is RNN. This is what we have seen, right? So when we get back, when we see AI, so first we started with machine learning as one subset of AI, right? After that, we have seen deep learning in subset of what? Machine learning. Basically, AI is a broad subject where we have machine learning as one subset and then deep learning as another subset of what? Machine learning. After that, what did we see? We will talk about different types of neural networks in deep learning again. So we have seen three basic types of neural networks, which are what? ANN, CNN and RNN. That was one part of the story. But in fact, we see many drawbacks associated with ANN, CNN and RNN as well. Okay. So when we discussed about the neural network, which is RNN, we have seen RNNs are used for text pre-processing, or RNNs are used for processing sequential data, that is text for example. So when we talk about this, RNNs have drawbacks. What were the drawbacks of RNN that we have seen? Vanishing gradients, exploding gradients, long-term dependencies, long-range dependencies and so on, right? So to overcome these disadvantages, we have seen two more modified architectures of RNN, which were called as what? LSTM and GRUs, okay? Even LSTM and GRUs have their own disadvantages, okay? So taking RNN as the base concept, using the deep learning model RNN, so we have advanced or the next level AI models, which are usually referred to as large language models. What are they called as? Large language models. So today we will be dealing with large language models and what are transformers and why do they called as large language models. What does the name says? Large language models. The models are huge. Okay, it means they have more trainable parameters. The capacity to handle the data would be more and the models would be complex as well, right? So as you can see here in the picture, it says machine learning is one subset of AI where machine learning will be dealing with algorithm that learns rule automatically from data. When we talk about deep learning, we say machine learning with what? Advanced algorithms using what? Neural networks. Okay. Now when I talk about large language models, what do you see there? There are also deep learning models, deep learning neural network for parsing and generating human-like text. So when we want to process the text data, when we want a model to act like human, understand the text like human, we go for next level of models, which are called as what? Large language models, which are again subset of deep learning models. Okay. Now Gen AI will exactly fit into this space. Okay. So when we talk about generative AI, what do you mean by generative AI? Generating new images, generating text. The machine itself generates the images. When you give some description, an image is generated. When you give some idea, the text is generated. Okay, you give a description about I want you to write a poem on sunset, sunrise, and something like this. Okay, so automatically the text would be generated. So with generative AI, the machine or the models have capability to generate the content. generate the data all by itself. Okay, so this has come into picture with the development of which models? Not the basic deep learning models, but with the development of what? Large language models. Okay, so as you can see, the boom in AI, the current boom in AI, where we use so many advanced transformers like ChatGPT, okay, Mistral AI, so many see, every field we have different transformer model which are being currently used. Okay, so that revolution in AI has actually taken place with the development of these large language models. Okay, so when I talk about Gen AI, we say Gen AI involves the use of what? Use of what? Same deep learning, deep neural networks to create what? New content such as what? Text, images or various forms of media. So generating data, generating new content with respect to what? Generative AI. So if you understand what are these large language models, you will understand what is actually happening in the current generative AI scenario. Are you all clear with this? Did you understand where LLMs fit? Okay. Now, so when we talk about text processing, we have seen RNNs. We have seen what? LSTMs, and then we have seen some mechanism called as attention mechanism in the last session. Using this attention mechanism and RNNs, we will develop this transformers. Okay, this is how the evaluation of RNNs have come into picture. Okay, first we study RNNs, LSTM architectures, attention mechanism, self-attention mechanism, and then finally the transformer models. Okay, so this picture already we have seen. Okay, so starting from 1990 era, so first we have RNNs, LSTMs, GRUs, and then we have the basic attention, okay, Bhaudanu attention, and then we have dot product attention, scale dot product attention, which we have discussed in the last sessions. Using that, okay, so the revolution of transformers have started developing since 2017. So we have again so many variations of transformers. For example, I say ChatGPT uses one type of transformer architecture. Okay, BART uses another transformer architecture. There are so many transformer based architectures are there with which different models have been developed. All that we will cover in today's session. Okay, so let's talk about LLMs first. Before we actually step into transformers, let's discuss about what are these large language models. What are different types of large language models which are existing, and how do we understand about transformers? Okay, most probably today would be entirely theoretical session because you have to understand the transformer concept in depth. Okay, so here RNNs comes into picture again, attention comes, self-attention comes, everything comes into picture when I talk about transformers. Okay. So what do you understand by large language models? The proper definition of large language models is like this. So large language models are nothing but the deep learning algorithms. They are also what? The deep learning algorithms equipped to summarize, translate, predict and generate human sounding text to convey what? Ideas and concepts. Are you all clear with this? So large language models are also what? Deep learning models. So the normal deep learning models just do prediction, right? But whereas the large language models not only do prediction but also what? Summarize the data, translate the data, generate human sounding text to convey some ideas and concepts. Okay, so this is how the language models have evolved. Okay, so when we talk about language models, the input data that I take here is what? The text. Okay, so will a machine learning or deep learning model understand the natural language? No. So we have seen word embeddings, tokens, word embeddings, all that in the previous session, right? So what do you mean by tokenization? So we have two types of tokenizations again. If I give a paragraph, I divide that into sentences, which is called as sentence tokenization. If I give a sentence, I divide the sentence into words, which is called as what? Word tokenization. Why do we have to divide the sentence into tokens? Because each RNN will process only one input. Each block inside the architecture will process only one input. Hence, we divide the entire sentence into what? The tokens. So each token again is an English language, okay, which will not be depicted by the model. So what do? we convert these tokens into what? Word embeddings. Okay. Did you study this or not in the last sessions? Yes. So we take the sentence as input, convert that sentence into tokens, give the word embedding form of these tokens, and then process that particular word embeddings, right? So first we studied about, we also have many word embedding algorithms like word to vector. What do you mean by word to vector? Representing the vector representation or matrix representation of the words. Okay, so we have fast text, we have glow, we have word to vector, so many different algorithms which are actually existing, which will perform word embeddings. Okay, for using word embeddings we have different algorithms, that is not part of a context, just understand what word embeddings are. Okay, so using this concept of word embeddings and tokenizations, we process the text using RNN or LSTMs, and then we have this transformers coming into picture when we talk about processing the text data. Okay, now we have again different types of transformers. So actual concept of transformers have come into picture in 2017 with the evaluation of attention is all you need. Okay, so how many of you have read that paper? Already you have completed attention mechanism, right? How many of you have read that paper? Attention is all you need. Nobody? Okay, okay, that is fine, but at least today, once you go home, please download that paper, or else we'll download it and share it in the group. Go through that paper. Okay, if you don't understand, see, understanding that papers gives you more in-depth insights of how transformers are developed. Is that clear? So please make sure that you download that paper and understand what is there in that paper. Okay, so we have so many advanced transformer models, like first one is BERT, bidirectional encoder representation of transformers. Okay, so this is one type of transformer model. Okay, and then we have T5 transformer, GPT, generative pre-trained transformer, which all of us use, ChatGPT. Okay, and then we have different versions of ChatGPT 3 in 2020. Before that we have 2, 2.0, and then 3, 3.5, and currently we have 4, 4.0 also, right? So, and then we have pathways large language models, advanced models, which are most probably used in medical applications. So depending upon different field, we have different transformer models which are developed and then currently in use. Few are open source, few are not open source. Okay, and then we have BARD and GPT-4. Okay, now when I talk about all these models, T5, BERT, BARD, GPT, Llama or Palm, all these are transformer models only. Okay, all these will have the same mechanism that I'm going to teach you today. Okay, except that the basic architecture of transformer will have encoder and decoder blocks, whereas few transformers are only encoder based transformers, few transformers are only decoder based transformers, few transformers have both encoder and decoder, which is what we will see. Is that clear, everybody? So the internal architecture would be different. Okay, so all of them in common have encoder, decoder. Some architectures will have what? Only encoder based architecture. Some architectures will have what? Decoder. Is that clear, everybody? So if you understand the internal mechanism of how encoder and decoder works, you'll be able to understand different architectures. Okay, all these are transformer models. The one in blue that you see are all transformer models. Okay, now as you can see, the evolution of large language models have taken place, something like that. Okay, so starting from 1988 RNN, 1997 LSTMs, 2017 transformers, and then we have GPT, the basic GPT in 2018, and then in 2019 we have GPT-2 and other versions of BERT. Okay, so we have this very wonderful pre-trained model which is called as BERT, bidirectional encoder representation of transformer, and we have different versions of them. We have Alberta, we have Robert A. Okay, so for when I talk about large data, okay, I go for distill BERT. Okay, I want more filtering. Okay, we go for distill BERT. Roberta, okay, robust data. When I want good accuracy with small data, we have different, depending on different applications or different data that we take into, we use different versions of BERT. Okay, similar to like different versions of ChatGPT. Okay, we have GPT-1, GPT-2, GPT-3, GPT-4. See, the number of trainable parameters in each version is more. Okay, so as the technology is advancing, okay, so as the data is gradually increasing, we have to develop the models which can take huge data, which can process more data. Obviously, the computation cost would be more when I talk about huge data, but then the advancement in technology have taken rapidly a huge growth where we need advanced or high level models. Okay, so in GPT we have different versions. Similarly, in BERT transformer also we have different versions. Okay, so as you can see, Robota, XLNet, all these are different versions of BERT models. Okay, we have so many others also which are not mentioned here. Okay, and then 2020 we have GPT-3, 2021 we have GPT 3.5, and then in 2022 we have this PALM, okay, pathways large language models, and in 2023, since 2023 again we have llama, we have GPT-4, PALM 2. So as you can observe, every year the growth has been so rapidly increasing that we have different versions of the base models. When I talk about different versions of the base models, the number of trainable parameters are huge. Okay, so it can accept more amount of data. It can give you good results. You can observe the difference between ChatGPT 3, 3.5 and the 4 if you have the paid version. Okay, there are so many new features that have been added into the models, the transformer models with which you can do a lot of things, right? Okay, so this is a complete picture of so many transformer models which are actually existing. I know the picture is not that clear. So as I told you, we have different versions. I myself doesn't know so many names, because when we talk about medical applications, or when we talk about pharma field, when we talk about different areas or different sectors of science and technology, they use different types of transformer models which we actually don't know. We mostly talk about GPTs, we mostly talk about BERT or the basic transformer models. But other than that, okay, so we have PALM, we have llama, so many different types of transformer models are existing. But no matter what model we talk about, the architecture would be same. Okay, so if you understand today's lecture where we talk about how the transformers are actually developed, or what is the internal architecture of transformer, how the transformer works, what is the main working principle behind transformers, you will understand about any architecture. Okay, so don't worry about what architecture or what type of transformer in which field it is being used. Understand the basic functionality of the transformer model. Okay, so when we talk about the optimal long language models in 2022 to 23 24, the last year, okay, the statistics have been taken from November 2024, the recent, okay, couple of months back. Okay, so as you can see, GPT-4 estimation is 1.76 trillion trainable parameters. You can just imagine 1.76 trillion trainable parameters on that. Okay, so we have stable LLMs, we have llamas, we have so many advanced, llama 2, okay, we have PALM 2. Okay, there are so many advancements that have taken place with OpenAI, the Google, okay, DeepMind of Google. Okay, so many algorithms on transformers have are coming into picture. Today you see one architecture, tomorrow you see the new one. Okay, but understand that the functionality or the understanding of the transformer would be same with some minimum changes to the architecture. Okay, now as you can see, there's a law called Moore's law, NLP's Moore's law, which says what? Every year the model size increases by tenfold. Every year the model size increases by what? Tenfold. So clearly you can understand the basic transformer 0.05 billion parameters. Next, when I talk about ChatGPT, 0.1 billion parameters. When we talk about ChatGPT by OpenAI, when we talk about, see, understand the two most important transformers that I keep on discussing in my sessions. One is BERT, one is GPT. Okay, BERT is by Google, GPT is by OpenAI. Okay, GPT we all of us use, right? So BERT, the BERT model, BERT transformer model by Google has how many trainable parameters? 0.3 billion trainable parameters. Now when I switch on to again GPT-2, the next version of the OpenAI, how many trainable parameters? From 0.1 it has been increased to what? 1.5 billion trainable parameters. And then as you can see, next In 2021 or in between that, we have GPT-3 where we have 170 billion parameters. See the way the model size are gradually increasing. Okay. The same thing again. Okay. So GPT-4 has what now? 1 trillion. Billions is gone. GPT-4 has how many trainable parameters? 1 trillion. As you can observe the graph. Okay. So 3.5 billion, 2 billion, 2.5 billion, 17 billion, 175 billion to gradually what? 1 trillion. This is 2024. In 2024. In 25, by the end of this year, once you learn transformers, you may have one more version with what? 100 trillion or more than that, I don't know. Let's wait for that and see. Okay. So where do we use LLMs? This is all about the evolution of LLMs. Okay. So where are we using LLMs? Everywhere. Where are we using LLMs? Everywhere. Okay. When you talk about AI, it is what? A LLM model, large language model. Basically, again, typically a transformer model. Okay. Now, all the large language models are basically classified into or categorically divided into 3 different types. Okay. One is pre-trained models. They're already trained. Okay. We just use that, give our input data, fine tune as per our requirement, and then generate the outputs. Okay. So when we talk about pre-trained GPT models, okay, are you developing anything in GPT? We are just using it, right? For our application, we are just using it. So we are fine tuning it as per our requirements and then using it. So these are called as what? Pre-trained models. And then we have another type of models which are called as multi-model. Okay, generating images, generating voice. Okay, where media comes into picture, not just text. When you talk about media coming into picture, we talk about multi-modal LLMs. Okay, what do you mean by multi-modal? Having voice, having images, having video, having text, all this combined together, different types of media combined together, we have this multi-modal large language models. Okay, and then we have fine-tuned models. Okay, they're also pre-trained models. You can have some adjustments and tune your model as per that. Okay, now when we talk about how do we work with LLMs, okay, so I say LLMs work in 3 stages. How many stages, guys? Are you all sleeping or are you all listening? If you don't understand this, you're gone. Because all your exams, all your projects in 2, 2, 3, 1, everything would be on transformers only. So it is mandate for you to what? Understand this. Okay. Now, what do you see here? I say when I talk about building LLMs, we have 3 stages. So what is stage 1? What is stage 1? Building an LLM. What is stage 2? Foundational model. What is stage 3? Classification. What is stage 1? What is stage 1? What is stage 2? What is stage 3? Classifier. Okay. Let's look into each stage. Let's look into the steps in each stage and understand how the transformers are actually developed. Okay. Now when we look into stage 1, what is step 1 in stage 1? Data pre-processing and sampling. What is this data pre-processing? What is this data pre-processing? The data that we usually get is very raw and unstructured, right? So there's no use that you develop very big model with 1 trillion parameters and give some raw data, right? So for this we go for what? Data pre-processing, tokenization, stemming, lemmatization, name entity recognition, okay, word embeddings, all these comes under what? Data pre-processing, which we have seen in our last sessions, right? So that is step 1 as soon as we receive our input data. What do we do after that? We use this mechanism which is called as what? Attention mechanism, okay. Using attention mechanism, we develop what? The LLM architecture. Okay, so this is stage 1. What are we doing in stage 1? We take the input data, we pre-process the data, apply attention mechanism to the data, and then attention mechanism QKV. What is Q? Query key value pairs, generation of that. I'll repeat it once again. Don't worry about it. Okay. So we generate these QKV values and perform so many operations on that, and then we try to develop the LLM architecture. This is stage 1. Okay. Once I'm done with stage 2, what do? We try to do pre-training. Okay. So when I talk about pre-training again, I'll have to choose a model on which I have to work on, and then I train the model, I evaluate the model, okay, I load the pre-trained weights which are already existing, and then I'll go for fine-tuning. So there are two things here, pre-training, fine-tuning. What are the two steps after the basic pre-processing? Pre-training, which we do in stage 2, fine-tuning, which we do in stage 3. When I talk about fine-tuning, let's say I have sentiment analysis task. Okay, what do you mean by sentiment analysis? Given text as input, my output would be what? Positive, negative or neutral. So this is the class. Okay, I am fine-tuning it to 3 different outputs. What is one? Positive review, negative review or neutral. When I talk about language translation, what would be the input? A sentence. What would be the output? A sentence again, in different language probably, right? So sentiment analysis takes input text as sentence and produces some class outputs, whereas language translation model takes text as input and produces text as output. So this is where the fine tuning is differed, that is classification, types of classification is actually differed. Got it, guys? So how do we develop LLM in 3 stages? First we read the data, pre-process the data. Next we pre-train the data, pre-process the data, use attention mechanism and then try to develop the LLM architecture. After that we pre-train the data, and after that in stage 3 we fine-tune the data. These are the 3 broad steps that we usually employ when we design what? Large language models. Okay. Now when we talk about large language models, what is the large language model that we are going to discuss in our session today? Transformers. Okay. Which large language model are you going to discuss? Transformer. Okay. Now what is a transformer? Read that. What is a transformer? Transformer is a deep learning model. Transformer is what? It's a deep learning model introduced in which paper? Attention is All You Need paper by Vaswani in 2017. The basic transformer paper is what? Attention is All You Need. Okay. It replaces what? The basic recurrent layers, RNN layers or LSTM layers with which mechanism? Self-attention mechanisms, allowing for what? Parallel processing and long-range dependencies. Okay. Now let's get back. When I talk about RNNs, how do the input data gets processed? First I take one word. Do you remember my class? First I take one word, X of t. I generate H of t. Yes or no? Let's say my sentence is I am ASHA. What is the first word here? I. So this is called as what? X of t. From this I generate H of t, which would be I. And then my next input would be what? Am. Now what is X of t? Am. I would be what? X of t minus 1. Okay. Now for the next layer, what would be the input? I from the H of t minus 1. Am from X of t. Yes or no? So how RNNs process data? One word at a time, that is sequentially, not parallelly. So first I word would be given, hidden state would generate something. Next the second word would be given, which will combine what? The first word from the previous state and the current input. What will happen in the third state? I have ASHA. So what is from the previous hidden state? I am. So this I am from the previous hidden state would be combined with what? ASHA in the current state. So what is the sentence that is generated? I am ASHA. So how am I processing this sentence? Sequentially, that is one word at a time. If it is 3 words, for 3 words I have to wait for 3 blocks to process. If suppose I want to process one whole textbook with some 1 million words, so will RNNs work? Same thing. What are the problems of RNN that we have discussed? Vanishing and exploding gradients, long range dependencies also. Yes or no? For example, when I say I am Asha, that is fine. And next when I say I am Asha, Asha is teaching. Okay, what do you mean by this? One sentence says I am Asha. The second sentence says Asha is teaching. So is that necessary that Asha is represented again? In general, how do we write this statement? She. Okay, so the context word she means what? She refers to Asha. So how would the machine predict that she here? From the previous sentence. Is it clear? So the context dependency will take place with respect to which mechanism? Attention mechanism, which was not there in RNNs. Is it clear? So these were the two main drawbacks of what? RNNs. So removing these two main drawbacks, we go for what? Transformer model, which process the input tokens parallelly, such that we don't have the problem of vanishing gradient, exploding gradient, and we don't have the problem of long range dependencies. Okay, so how do you define a transformer model? So what are transformers? Transformers are the deep learning models which are introduced in the paper. Attention is all. So you have to remember, without attention is all you need. You can't say I know transformers, I know AI. It's like that. The current scenario is like that. Okay. So all of you, it is mandate for you to read this paper from beginning, first word to the end of the paper, and understand it very clearly. Okay. It will be more easy after the session today. Okay. Once you understand today's session, you go and read. It will make your job easy. Okay. So was introduced in attention is all you need in 2017, which replaces what? The transformer model replaces the basic RNN layers and LSTMs with what? The self-attention mechanism. Okay, with which we have parallel processing and long range dependence. Okay, so when we talk about transformer, the only transformer which we mostly know is what? Generative pre-trained transformer, GPTs. Okay, so what do you mean by generative? What is pre-trained? What is transformer? Let's split this into individual words and try to understand. What do you mean by generative? Generating something. Is ChatGPT generating something? Yes or no? Okay. What do you mean by pre-trained? Already a trained transformer is there. We are just giving a new input. It is generating the text. Okay. What do you mean by transformer? Transformer is an LLM model where it is transforming the data. I say, this is my current situation. Please draft an email. I am not able to attend today's class, so please draft an email. So it generates a text based on the given input. It transforms this given input into different type of text using the pre-trained model. So hence the name what? Generative pre-trained transformer. So when you look into those three words, what do you mean by generative? Can generate human-like text. Is ChatGPT doing that? Yes or no? How is that doing? By using this pre-trained models. Okay. So learns from huge data sets before fine-tuning. So I told you, right, LLM 3 stages. First is pre-processing. Second stage is pre-training. Third one is fine-tuning. So this pre-training and fine-tuning comes into picture here. Okay. That is pre-trained model. After that we fine-tune. What do you mean by fine-tune? Use it as per your requirement. Okay. So that is what being done in your transformer, which uses self-attention for efficient language understanding. So transformers has the capability of understanding the language efficiently as how humans understand and process the language. Okay. So these are all the things that we have to learn when I talk about transformers, which we will be covering in today's class. Okay. So on the right hand side, can you see a diagram or a picture? That is a transformer architecture. We'll see every part and block of it in detail today in the session. Okay. So what do you see there? You see two blocks again, right? Left hand side one block, right hand side one block. So one is encoder block, one is decoder block. Are you all clear with this? Are you all clear with this? So basically the basic transformer architecture is what? Encoder-decoder block. Depending on different types of transformers, they use only encoder, decoder or both encoder, decoder, that we'll see later. Okay, for now you just understand how is the internal architecture of transformer looks like? Encoder block, decoder block. So for understanding the entire functionality of the transformer, these are the things that we have to study. Okay, so let's see to what extent you have reached and what are the things that we will learn in today's session. Okay, so what is the first word that you see, guys? Are you all clear with tokenization? Yes or no? Let me repeat. What is tokenization? Given an input sentence, the input sentence would be divided into tokens. Okay. Next. What is the next one? Input embeddings. So, given the tokens are converted to what? The word embeddings, which are generally referred to as what? Input embeddings. Are you all clear with this? Yes or no? Okay. Next. What is the next term? What is this positional encoding? Each token, did you study this earlier? Okay. Each token that is generated will have a position. Such that when I say, I am ASHA, ASHA is teaching in the class. Okay. If the is repeated 2 times or 3 times, so we will not use different token or different word embedding for the, because the in the first sentence is same as the in the second. So we give one position for each embedding, that is called as positional embeddings, that we will see now. Okay, so you only know about what? Tokenization. You only know about what? Word embeddings or input embeddings. After that we do what? Position embeddings in transformers. Okay, and then we calculate the residuals. Residuals is what? Summation. For loss calculation and all that, we have to consider all the data points. So residuals. And then you know about query, key, value. Self-attention comes into picture here. Okay. Query, key, values. We add them and normalize the data here in transformers. I'll tell you why do we do normalization, what is all that. In the can you see that diagram? Add and norm is one step, that is in yellow. Okay. We'll study about every block and every point in very clear way today. Okay, don't worry about it. Okay. Now after that we have what are the two important blocks of transformer architecture? Encoder and decoder. We'll see what encoder does, what decoder does. Okay. After that, the attention mechanism, how self-attention is different from attention mechanism, what is multi-head attention, and then what is masked attention, encoder-decoder attention, how do we take the output probabilities, use softmax function for the same, and then how do we develop encoder-decoder models, and then how do we also develop what? Decoder-only models. Are you all clear with this? So this is the flow, or these are the terms that you have to understand when you learn transformers. Is that clear? ఈ వర్డ్స్ తెలిస్తే ట్రాన్స్ఫార్మర్స్ అర్థమవుతుంది. ఓకే, గాట్ ఇట్? సో టోకెన్స్, ఇన్పుట్ ఎంబెడింగ్స్, పొజిషనల్ ఎంబెడింగ్స్, residuals, query, key, value, attention, self-attention, adding and normalization, encoder, decoder, multi-head attention, encoder-decoder architecture, how the connection is made from encoder-decoder, how do we take the output probabilities by using softmax function, and then different types of transformer models, basically encoder-decoder models and decoder-only models. Clear? Okay. So as you can see, the LLM era or the paradigm shift in machine learning has taken place something like this. Okay. So in 2018 we have BERT, as I told you, different versions of BERT, right? Distill BERT, Roberta, Robust BERT, Alberta. Alberta is a light BERT. So mini version. Okay, mini version of the BERT model. Okay. And then Electra, DBERTA, so many different representations. Same model, different representation. This is one section. When you see on the right, generations, we have different generations. Okay, generative pre-trained transformers. We have GPT, GPT-2, GPT-3. In between we have GPT Neo. which most of us doesn't know. And then we have GPT 3.5, Llama, GPT 4. Okay. So we have different architecture representation. We have different generations of what? The transformer models. Okay. Now as you can see, the three different types of transformer models are what? Only encoder based transformer model, both encoder-decoder based transformer model, and then finally only decoder. Okay. So where is your chat GPT here? GPT is a decoder only based model. GPT is a decoder. Though we study encoder-decoder based architecture, GPT models use which type of architecture? Only decoder based architecture. When I talk about BERT uses which type of architectures? Only encoder based architecture. Then who is using encoder-decoder? BART. Okay, we have other models which uses both encoder and decoder based models. Okay. Now, what has caused this paradigm shift, or what was the need for LLMs? So we had problems in recurrent networks. What are the problems that we have seen in recurrent networks? Information is effectively lost during encoding of long sequences. This is long-term dependency problem. Sequential nature disables what? Parallel training and favors large or long time steps, right? So these were the problems of the basic recurrent neural networks, for which what was the solution? What was the solution? Attention mechanism, right? So what did we see in attention mechanism? Using attention mechanism, we can handle what? Long range dependencies. We introduce what type of training? Parallel training using attention, and dynamic attention weights based on inputs by taking into picture the query key and values. Is it clear? So why LLMs have come into picture? To overcome the disadvantages of what? The basic RNNs with which mechanism? Attention mechanism. Okay. So where do we use these LLMs or the transformers? When I have voice to text conversion, I give a voice, text should be converted. There we use transformers. The vice versa of it, give text, voice output. Give a text, generate an image out of it. Okay, and so on. Okay, so we have seen what are recurrent neural networks, how do they process, yes or no? X of t, h of t minus 1, where the new x of t would be what? X of t into h of t minus 1, and the process takes place. That is sequential operation. Okay, so we have seen these two problems. What are the problems? When we calculate the gradients in the backward propagation, the gradients either vanishes or explodes. Okay, when I talk about long range sequences. So this was the problem. Hence we have gone for next type of architecture, which was what? LSTM. Okay, so how does LSTM work? By having both hidden state and the memory cell. We have seen three gates, right? What are those three gates? Input gate, forget gate, and output gate. What does input, forget, and output gate do? They write, delete, and append the cells, right? To overcome the disadvantage of long-term dependencies, we have this input gate, forget gate, and output gate in LSTM architectures. Okay. To maintain long-term dependencies, which is never forgetting the memory cell. So we have seen this architecture, right? What does forget gate do? What input gate does, what output gate does, what would be the new cell content, what is the new cell state, what is the hidden state. All this we have seen when we talked about LSTMs in the previous sessions. We have also seen the internal architecture of how LSTM works with respect to which gates. Forget gate will have some cell content, it will compute the forget gate. After that, first we have the input gate, next we have forget gate, after that we forget the cell content, and then we write some data to the new cell content, and then we compute the output gate, and the output from that particular cell content with respect to hidden gate would be taken care of. Okay, so this is what we have seen when we talked about what? LSTM. Still LSTMs also have drawbacks, that also we have already seen. Okay, so finally we have come to this type of architectures which are called as sequence to sequence models. What are they called as? sequence to sequence models. Okay. So when I talk about sequence to sequence models, they are one type of recurrent neural networks which takes sequence as input, produces sequence as output. Chatbots, you give sequence as input, output would be what? Sequence. Text summarization, input is a big sequence, output would be a smaller version of it, but it is also a sequence. Language translation, input would be a sequence, output also would be a sequence. So basically, when I talk about the transformer models which takes sequence as input and sequence as output, we call them as what? Sequence to sequence models. Okay. So language translation, text summarization, chatbots, all these different applications uses which type of models, guys? Sequence to sequence model, where input is a sequence, output is also a sequence. Okay. So what is the input here? I am ASHA. In which language? English. So that is converted to which language? Hindi. May ASHA. Is it clear, everybody? So input here is a sequence in English language. Output here is also a sequence in some other language. So this is a language translation model. This is a language translation model. Okay. Now let's understand about the sequence to sequence model. Okay. If you understand sequence to sequence model and if you understand how encoder-decoder works, you'll understand transformer. So before we actually step into transformer, we will understand what? What is basically a sequence to sequence model, or how encoder and decoder works in a sequence to sequence model. Okay. So the sequence to sequence model is composed of what? It is composed of what? Encoder and decoder. Okay. What does encoder do? The encoder will process each item in the input sentence and it will produce a context vector. It produces what? A context vector. This context vector would be given as input to the decoder. That decoder will do the conversion. Okay. Now let's see this. What is being generated there at the input? Okay, let's go back. I'll repeat this again. Okay. So what is the input to the encoder? 3 dots. What is the input to the encoder? 3 dots. So encoder takes this as input and produces as output, which is called as context vector. Produces output which is called what? Context vector. As you can see, look at that. Encoder takes those input and generates what? Context vector. That context vector would be given to decoder, which will generate the output. So here the green dots are I am ASHA. The context vector is the embedding form of I am ASHA. And this embedding form of context vector is given as input to decoder, which will generate May ASHA who. Are you getting my point? So what is the input here to the encoder? I am ASHA. Where the output of the encoder would be what? A context vector of these 3 words. Okay. And then what would be the output of the decoder? May ASHA who. That is the language translation which is being done. Okay. Now look at this. Let's take one sentence. Okay, I have taken a statement there. Okay, what is that? J shoes etoident, something in some language. Okay, French or German or whatever it is. Okay, so here what will happen? This input would be taken by encoder as input and generates what? The context vector. Generates what? Context vector. How is the context vector generated? By tokenization, by word embeddings and all that, the context vector would be generated. And we have seen, right, each context vector will have n-dimensional space. So here how many dimensions am I taking? 4. I have 3 words and each word is represented in how many dimensions here? In fact, it would be the basic GPT-4 has 8192, 1024, 512 is basic. For our simple understanding, I have taken only what? 4 dimensions. Okay, are you getting? What are those 4 dimensions of the first word? 0.901 minus 0.651 minus 0.194 minus 0.822. These are randomly generated word vectors of what? The first word J, 4 dimension vector. Okay, so using this, I'll try to generate the output. How do I generate the output again? As you have seen, recurrent neural networks. One input would be processed sequentially. That is, first JE would be processed. Second, The second word would be processed where the both first and last word would be combined, and third word would be processed which would be attached to what? The one and two words, and the entire sentence would be processed. After that we get what? The context vector. So from where are you generating the context vector? From the last word. I process I first, and second, ASHA third. After I process ASHA, I will generate what? The context vector. This is encoder. So what does decoder do? Decoder takes what? This context vector as input and generate what? May, ASHA, who. Are you all clear? Yes or no? Okay. So this is what we have seen. So at each time step, the neural network will process each. As you can see, in the first hidden state, first word would be processed. In the second hidden state, second word. Third hidden state, third word. After third hidden state, I'll generate what? Context vector, which would be given to the decoder, where I am generating the output. Are you all clear with this? Yes or no? So what is happening here? Sequential operation. First hidden state will take what? The first word. Second hidden state will take what? The new word with the previous hidden state word. Third hidden state word will take what? The new word with previous hidden state words, and generate a context vector at the end. Are you clear? So this context vector is given as input to what? Decoder, with which the translation happens. So what is the output here for JSU sum that etudiant? I am a student. Is that clear, everybody? So this is how the basic encoder-decoder architecture works. Okay? Okay? Now, we have seen unrolling, right? What is the difference between this picture and that picture? Here I am taking only one encoder block and decoder block, okay, for basic representation. But when I talk about I am ASHA, how many words are there in the sentence? 3. So how many RNN blocks or how many encoder structures do I want inside? 3. Because everything is processed what? Sequentially, one at a time, right? So we have this unrolling. Look at that. First word JE is given to the first encoder RNN. Okay. Second with which I'll generate one hidden state. Previous hidden state and next word is given to second RNN, and that the hidden state decoder where I would be generated. After that AM would be generated, A would be generated, and a student would be generated. This is called what? Unrolling. Depending upon the number of input tokens I have, the unrolling happens that many number of times. Why do we take it as a simple closed structure? Because I don't know how many input tokens I have in the given sentence. So that is the reason initially I'll have a closed structure like this. Okay. So depending on the input tokens that I have this unrolling. Please read that statement at the end that I have written. This is called as what? Unrolled view, where instead of showing one decoder, we show a copy of it. What do you mean by copy of it? One decoder will take the first word, second decoder will take the second word along with the previous hidden word, third decoder will take the new third word along with what? The previous hidden state words. Okay. So we show a copy of it for each time step as we look at the inputs and output of each time step. Okay. Now, the main problem here is the context vector. This is basic RNN, encoder-decoder architecture of what? RNN. The problem with RNNs here is the context vector. What was my input statement? I am ASHA. Okay. So for I have a hidden state. For AM, I have a hidden state. For ASHA, I have a hidden state. But how is the context vector generated? Only from hidden state 3. I am not generating context vector at every hidden state parallelly. I am generating context vector only after I process I, AM and ASHA. So this is the bottleneck. This is the bottleneck because the context vector is generated not for every token. The context vector is generated at the end of the encoder. Andukane we have this problem of what? Long range dependencies. Okay. Is it clear? So for overcoming this disadvantage of the basic sequence to sequence model where the encoder generates only one context vector at the output, we have the next model which is called as what? Read the first point, guys. The context vector turned out to be the bottleneck. What do you mean by bottleneck? The drawback of the previous basic sequence to sequence model. So it made more challenging for the models to deal with what? Long sentences. Hence, a solution has been proposed. Okay, you can read this paper also. Okay, in Badnau paper, okay, or Long et al. In 2014 and 15, these papers, they have introduced a technique called what? Attention. So in which what happens? Attention allows the model to focus on relevant parts of the input sequence. That is, I want my context vector to be generated after every hidden state, not at the end. Is it clear? So I am ASHA, the context vector, not like that. I, a hidden state, am a hidden state, ASHA, a hidden state. All these three hidden states has to be processed by the decoder, not just one hidden state at the end. So that is the idea behind what? The attention mechanism, with which all the relevant parts of the input sequence would be processed. Okay. Now as you can look at this, look at the difference here. First I am taking the first word, I generate a hidden state. Second word, hidden state. Third word, hidden state. Look at this. What am I doing here? Am I taking only one context vector here? No. What am I taking here? With attention mechanism, I want relevant information of all the tokens. Hence, I am doing what? Look at the between one, the output of the encoder here. Previously, I had only one context vector, but here what am I generating? Three context vectors because I have three words. I am ASHA, or these three words that you take. So, based on this, the attention, see, I have changed the word in the decoding stage. Previously, it was only decoding. Here it is what? Attention decoding. If you have only one context vector in between as the output of encoder, we call it as normal decoder. But here, the output of encoder is what? All the hidden states. Hence, in the decoder, I call it as what? Attention decoder stage. Are you all clear? Are you with me, guys? Are you understanding this? Yes or no? Okay. Now look at this. An attention model, this is very important. An attention model differs from a classic sequence to sequence model in two ways. Please understand these 2 points. What is point 1? First, the encoder passes a lot more data to the decoder. What do you mean by lot more data? The entire context vector, everything is processed at once. Okay. Instead of passing the last hidden state of the encoding stage, the encoder here passes what? All hidden states. This is the first difference. Did you all understand this? Instead of passing one hidden state at the end in the normal sequence to sequence model, what am I doing with attention? All the hidden states are passed. Second point. Secondly, an attention decoder does an extra step before producing the output. What is that extra step? What is an extra step? Do you observe an extra step here? End of the token. Okay, there is a call EOS. Start of the token and start of the sentence and end of the token would be added. Okay. So this is the difference between the basic sequence to sequence model and attention based sequence to sequence model architecture. Okay. The attention decoder RNN takes what? End token at the end. This is the difference. Okay. So the transformers are actually evolved with respect to what? This paper, which is called as what? Attention is. It is okay. So what is attention? What is sequence to sequence model? What is the difference between the basic sequence to sequence model and attention based sequence to sequence model and all that. Okay. So attention is all you need. The transformer has taken a huge change. Okay. So these are 4 things that we will learn today when I talk about transformers. What are those 4 things? Embeddings, attention mechanism, and then the multi-layer perceptrons, the same ANN. See, I told you in the beginning only when we were talking about ANN. You may have different types of architectures, but at the end, we again use the same thing. Same forward propagation, same loss calculation, same backward propagation everywhere. Even in RNNs, it is the same. Even when you go for attention or transformers, it would be the same. CNN also it was the same, right? We take input image, we go for convolution operation, we go for pooling. After that we give it to what? Fully connected. Similar to that, in transformers, we take the data as input, text data as input, we do text pre-processing, give it to attention, and then after that we have again feed forward network only. Is that clear? So ANNs will not leave you here. Wherever you go, ANN follows. Okay? So even in CNNs, we have convolution, pooling, fully connected layer. In RNNs, we have data as input. In encoder-decoder, we have what? Self-attention and then feed-forward network only. Is that clear, everybody? Okay? So that is what MLP is all about. Multi-layer perceptrons. After that, we go for unembedding. We go for embedding, and for translation, again, we go for unembeddings. Okay? So these are 4 important concepts that I would talk about when we start actually the transformer structure. Okay? So what do you observe here? I gave a sentence. Okay, what is the sentence? The day to take the cleverest thinker of all time was... so this is which problem statement? You have done an exercise. Next word prediction. Very good. Okay. So in order to predict next word, what do I do first? First I divide the entire input sentence into what? Tokens. After I divide them into tokens, what do I do? Put embeddings. So when I take an input data, it might not only be a sentence. It can be an image. It can be a voice data also. What happens when I take an image? See, if it is a text data, I divide that into tokens. If I take an image for a transformer model, what does it do? It divides the entire image into some blocks, as you can see. This is the image. The image has been divided into these tokens. When I talk about audio data, the data would be divided into some chunk of data, right? So when I talk about transformers need not take only text data. Transformers will also take what? Image data. Transformers may also take what? Voice data. So tokenization is done everywhere. What we have seen is word tokenization or sentence tokenization or text tokenization. Apart from that, you will also have to perform image tokenization and voice tokenization if you take different types of inputs. Of course, that is not our context as of now. We will deal only with text data in our sessions. Okay, but just for your understanding, you understand that tokenization refers not just to the text but also to any type of input data that we take. Okay. Now, after we do tokenization, what do? Word embeddings of n dimensions would be generated. Okay. After that, we apply what? We give that to attention mechanism. After attention, why attention mechanism? Why attention mechanism? Why so many embeddings? See, I can take only 4 embeddings. No, what is the need for 512? Why this ChatGPT 4 or GPT 3 has 81921024 embeddings? See, understand this word. Please understand my point very carefully. If you understand this, you'll understand everything. Okay? So, we know that we take a sentence as input. We convert that input sentence into tokens. Tokenization is very easy. We will all do that. Second step after tokenization is what? Word embeddings. So, we say each word is embedded into n-dimensional vector. Why? Why that n-dimensional vector? Yes? Anybody please? See, when yes? Very good. 100% correct. Okay. A word may have different interpretations. Interpretations. Okay. So, that depends upon the sentence that I use again. For example, let's talk about a word called bat. What is bat? One is cricket bat, animal bat also, the bird or animal, whatever it is. Okay. So, how do you define whether it is a cricket bat or whether it is that animal bat? Depending on the sentence or the word that I am talking about. If I say today there is a match, Virat Kohli was using his bat very efficiently. So, this bat refers to what? Cricket bat. Okay. Today I came to college, I was watching cricket. I also saw a bat on the tree. I also saw a bat. We'll refer to again the cricket bat until and unless the word tree comes into picture again. Yes or no? What is the sentence that I am giving, guys? I came to college today. I was watching cricket. All of a sudden from a window, I saw a bat on a tree. I saw a bat on a tree. So what is this bat representing here? Ikkada cricket kuda undi. Ikkada bat kuda undi. Ikkada tree kuda undi. So what is this bat is referred to? This bat refers to animal because I say I saw a bat on a tree. Cricket bat won't be on a tree. That is basic common sense. Right? So as humans we will understand this context. As humans you are able to, when you process the data, you also have to ensure your model understands the context of the word in the given sentence, for which we will go for different probabilities. The more the length of the embedding dimensions, the more detailed analysis of the data would be done. Yes or no? The previous ChatGPT version has very less dimension vectors. Hence, the output was not that accurate like what we see now. Okay, this is achieved because of what? More number of dimension vectors added. So again, there's a drawback of this. What is the drawback of this? More dimensions you add, obviously what will happen? Your CPUs, GPUs will not work. You have to go for TPUs. Okay, we have NPUs now, neural processing units, not even TPUs. Okay, so more advancement, more good predictions, along with that more computational cost is also involved. So that is the reason we say we can't manually or develop, I can't say develop transformer from scratch like how we have done for ANNs or CNN. We just pre-train and fine-tune the transformers. Are you all getting me? Yes or no? Did I say we are developing transformers from scratch like how we have done for ANNs and CNN? No, we can't do that because we don't have. See, simple is what? Only 4 dimensional vector or 6 or 10 తీసుకుంటాం. I can't even process 512 dimensional vector using the normal CPU systems that we have. Okay, so the complexity increases. So why do we use n dimensional vector, guys? To understand the context of the word in that particular given sentence. Okay. Look at this. What do you see here? Model. What is that first model? What is that second model? The first is a machine learning model and second one is what? Both are models only. But how will we understand that model and this model? With respect to the other words in the sentence. Okay. This is the 3D architecture or 3D view of transformer. So what are we doing? Take the input sentence, forget about the model. Come to transformers. Okay. We take input, we take word embeddings, we apply attention mechanism and we give it to what? Multi-layer perceptrons. Are you all clear with this? Yes or no? So 4 steps. What are they? Take the input sentence, tokens, word embeddings, give it to attention mechanism, and then what? Multi-layer perceptrons. Are you all clear with this? Okay, look at this. Many repetitions. What do you mean by many repetitions? We don't have only one encoder. We have many encoders, we have many decoders. So many repetitions of this would be done. Of what? Tokenization, embeddings, self-attention, multi-layer perceptron. So many repetitions concatenated together will have the entire transformer architecture. Okay. So we have seen what attention mechanism is all about. What was attention mechanism? Assigns what? Attention weights to each word to know how much attention the model should pay to each word such that the exact context of that particular word would be depicted. Okay, so we have already seen, okay, in the original paper, how does RNN works, how attention mechanism is, I don't want to repeat this. Okay, so these are 2 things that I would like to focus today in this session. The attention mechanism, which is called as what? Scale dot product attention, and then we are using scale dot product, I give it to what? Multi-head attention. Okay, QKV values calculation, We have already seen. Yes or no? In the attention, I don't want to repeat it and waste time because I have so many other topics to discuss. Okay. After that, we go for what? Scaled dot product calculation. 5 steps. What is step 1? Query of the first word, embedding of the first word, that is x1 and q1. Along with that, we generate weights, right? After that, what do we do in step 2? Q, K transpose, and we perform what? Q into K transpose, query into the embedding matrix. Okay. After that, what do? We divide that by dimension. That is Q into K transpose by square root of dk. D represents what? The dimension of the vector that we have taken. This is step 3. What do we do in step 4? Apply that to softmax function. That is QK transpose by square root of dk on softmax applied to that. After that, what do? We multiply that with values, hence we generate the output. This is what we have seen in the last session, right? Attention mechanism. Next, we give the scale, concatenate it to more, and then generate what? Multi-head attentions. Okay, 1x is replaced by what? x1, x2, x3. More words, more concatenations, and that is given to what? Multi-head attention. Can you see that concatenation? A1, A2, A3. What is A1, A2, A3? Attention weights that are being calculated. Okay. Now look at this diagram. Okay, what do you observe in this diagram? Let's divide the diagram into 2 blocks, as I told you. Encoder and decoder. First observe the encoder. What is at the bottom of the encoder? Inputs. We know. Second, input embedding. So the new concept that I told is what? We give positions to these embeddings. Okay. So that is given to what? Multi-head attention. Normalization is done and that is given to feed forward network. Now listen to me very carefully. I am concluding this. I'll give you a break and then let's join back. Okay. The attention works something, the transformer, the encoder works something like this. It's take input, generate the tokens, input embeddings are generated, they're given some positions. After that, attention is applied. What attention? Multi-head attention. Scale dot product, multi-head attention. I perform normalization and then I give it to what? Feed forward neural network from where I generate the output. Is that clear? Malli in depth ga okokka step how tokenization is done and all that we will see once you take a break. Okay. So we will analyze this architecture after the break. Okay. How input, what is transformer encoder, what is transformer decoder, how encoder works by taking the input and what are the outputs that are being generated. Let's take a break for 10 minutes. Yeah. So we'll continue. So where did we stop? Architecture of transformer, right? So what are the 2 important blocks that you see in the architecture of a transformer? Encoder block and decoder block. Okay. So we'll try to focus on each block in separate. Okay. Now as you see, let's get back to this again. Okay. Let's get back to this. So where did we reach till now? We know what is tokenization. We have seen embeddings. We have seen position embeddings, residuals. I'll explain you about residuals. Okay. And then we have seen query, key, value application, normalization, encoder block and decoder block. Okay. Yes or no? So we are up to this now. Okay. Now let's see encoder and decoder blocks in detail. Okay. Now when I talk about encoder and decoder block, they are not just one. Depending on the architecture that we use, GPT-4 has n number of encoder blocks, GPT 3.5 has n number of encoder blocks. Okay, that is different part of the story. Okay, so let's see how does the basic 6 block or the first basic transformer architecture of 6 blocks looks like. Okay, so as you can see here, the original transformer paper was published in Neural Machine Translation Model. After attention is all you need, there is another paper called Neural Machine Translation in which the first transformer was designed. Okay. So, first is attention is all you need, where we had this attention mechanism which will remove the drawback of one context vector getting generated at the output of the encoder. which is replaced by multiple hidden state, where each token will have the hidden state generated, which would be given to the decoder block. Okay, this is attention mechanism. After that, in the first paper, when we talk about transformer paper, so that is the neural machine translation, language translation, first transformer model. Okay, where input would be some sentence, output would be some sentence of different language. Okay, now when you see, this is the architecture of the transformer. Okay, the broad architecture of the transformer looks like this. Okay, so we give the input to which block? The encoder block. Encoder block generates what? The features or the hidden states. We don't say context vector because we have different hidden state, hence we call it as what? Features. And these features are given as input to what? Decoder. From decoder we generate what? Outputs. So this is the overall block diagram of what? The transformer model. Okay. Now, as you can see, when I talk about only the encoder, what is encoder actually doing? It takes the input, process that input, and give that particular hidden states as output to the decoder. Okay. Now, as you can see, the encoder in the transformer consists of what? As I told you, there is not one encoder block. There are multiple encoder blocks, and input sentence go through all these multiple blocks. Input sentence goes through what? All these multiple blocks, and output of the last encoder block becomes what? The input features, which would be given as input to the decoder. Okay, when I talk about encoder, just understand that there is not just one encoder. We have concatenation of multiple encoder blocks. Okay, similarly, the decoder also contains multiple decoder blocks from where we generate the output. Okay, so this is how the architecture looks like. Got it? So each decoder block receives what? The first one is encoder, the second one is decoder. So encoder takes the input and generate features. The features are given to what? Each decoder block. See, look at that. Feature is not just given to first decoder block. Features are given to what? All the decoder block. Hence read that statement. Each decoder block receives the features from the encoder. Okay. If you draw the encoder and decoder vertically, the picture will look like this. This is from the paper. Okay. Now let's look into this first part. Okay. So let's look into encoder. So once I give the input, what is step 1 that happens? Tokenization. Okay. First we take the input, generate the tokens, and after tokens we generate what? Word embeddings. So tokenization plus word embeddings, let's consider it as step 1. Is it clear? So once you take the input sentence, we convert that sentence into tokens and perform and obtain the embedding dimensions of that particular token. That is called input embeddings. After that we do what? After that we calculate what? Positional embeddings. Positional embeddings. Okay. We combine these input embeddings with positional embeddings. Hence there is a concatenation symbol there. Can you all see that? Yes or no? Input, word embeddings, concatenated with what? The position. I'll tell you what with an example. Just understand this diagram for now. Okay. Now this is given to which block? Encoder block. This is data pre-processing. In LLMs we have seen stage 1, stage 2, stage 3, right? In stage 1 there were 3 steps. What were they? Preparing the data. Second one? Not second stage. In stage 1, first step was preparing the data. Second step was what? Attention mechanism. Third step was what? LLM architecture. So the down one that you see is what? Step 1 in stage 1. That is pre-processing. What is step 2 in stage 1? Attention mechanism. That will happen where? In the encoder blocks. Are you all with me? Yes or no? Okay. Now with the transformer we inject what? Positional encoding into each embedding so that model can know word positions without recurrence. As I told you, if the is repeated n number of times, I can't take the as new word and generate new token every time. There would be only one token generated for the word the. That is, I want to generate unique tokens from the given sentence, because to avoid the processing. See, the may be n number of times, and may be n number of times, of may be n number of times. The and of, even if they are repeated 10 times, they hold the same meaning. Yes or no? So I don't want to generate new embeddings for that. I don't want to reoccur the words again and again. For which we use what? Positional encodings. Okay. Now the input to the transformer is not the characters of the input text, but a sequence of what? But the sequence of embedding vectors. This is step 1. Okay. So we are trying to decode the transformer architecture into encoder and decoder. In encoder again, when we take the input, we take that input and convert that into tokens and then obtain the n-dimensional vector space of that particular tokens and also generate what? The positional embeddings of that. Okay, this is something new. Generating positional embeddings is new apart from what? Generating embeddings. Okay, so once you are done with that, we give that to the encoder block where it generates features. From there we go for what? Decoder block where we obtain what? Softmax and output probabilities. I want to know the probability of each word having probability. Suppose if I want to predict a new word, like the example that we have seen, okay, there would be so many words generated, but the word with highest probability would be chosen as the output, right? So we will connect the decoder block to what? Softmax and output probability to generate the output sentence, okay. And then when we talk about decoder outputs, okay, so as encoder takes simultaneously, as encoder takes the input simultaneously, decoder will also generate one output at a time, okay. Now look at this. If suppose I have a sentence called I am ASHA, okay. Now first I read I, second I read am, which is concatenated with the previous hidden state. So for the second step, time step, I have I am. In the third time step, I take a new word called am, which would have the previous hidden state I am. So what is the output of the encoder here? I am Asha. If suppose I take a new sentence, I again concatenate that new sentence to this new word. Okay. So this is called as auto-regressive. Auto-regressive. This is reading from the previous and adding that to the weight. Okay. Now, at the end, what did I tell you? When we talk about decoder module, when I start translating, do I have output for the first word? What would be the output of the first decoder module? We don't have anything initially. So we take one token which is called as what? SOS. What is that SOS represent? Start of the sentence. Okay. Similarly, we'll end that with what? EOS, which represents what? End of sentence. Okay. So this is something new that we instantiate when we talk about the decoder block. Okay. So the decoder uses what? Multiple decoder blocks, which we have already seen. Yes or no? So the encoder has multiple encoders connected inside that. Similarly, decoder will also have what? Multiple decoders connected to it. Okay. So when I talk about this, okay, SOS and EOS. Okay. After SOS would be given at the start of the first decoder block and EOS would be given at the end of the decoder block. Okay. So the output of the decoder would be given to what? Linear layer, and then I give it to the activation function softmax where I'll try to predict the output probabilities. Okay. Now look at this. Okay. I have put it all together. So this is the basic architecture of the transformer, whereas we take encoder and decoder. Okay. So what is step 1? Inputs, word embeddings, which are added with what? Concatenated with positional encodings, and then the output of this word embedding and positional encodings are given to encoder block. Given to what? Encoder block, which generates what? Features. Why am I representing NX there? N number of encoder blocks. That may be 6, 512, 1024, 8192 or N, depending on the type of architecture or version or generation of transformer model that we consider. Okay. And then the output of the encoder would be what? Features. The output of the encoder would be features, which are given to what? The decoder blocks. All the decoder blocks. The feature is not just given to one decoder block. The features are given to all decoder blocks, and the output of that decoder block is given to linear softmax for output probabilities. Got it? Yes or no? Okay. Now let's study about that encoder block in detail. So this is the overall picture or the rough picture of the transformer, where we have input taken, encoder block, features generated. The features would be given to decoder. Decoder is given to what? Softmax, linear, softmax and output probabilities. This is the entire picture. Now let's understand the main operation of the transformer, understanding what happens inside the encoder block. Did I explain you what is happening in the encoder block? I just told you what? It takes what? The word embeddings and positional embeddings and generates what? Features. This is what I told you. Now we will see how the encoder blocks takes this word embeddings, positionals and generates what? Features. That is what we will see now. That is, we will understand encoder block in detail, what is happening inside the encoder block, and also we will understand what is happening inside the decoder block. Are you all with me? Okay, now let's see this. So what is happening in the encoder block? As I told you, encoder block uses which mechanism? Self-attention mechanism. Which mechanism? Self-attention. So as you can see, I am taking inputs. I am changing the diagram again. I am taking the inputs. When I say inputs, I mean the tokens of the inputs. I mean input word embeddings along with what? Position. So can you see that in blue at the bottom? So when I say input, what am I referring to? I am referring to word embedding with positional embedding. That is given to encoder block. And what is the first step of operation that is happening in the encoder block? Self-attention. Which mechanism? Self-attention. That is multi-head. All self-attentions together is multi-head attention. I'll explain you that. Okay. So the encoder block uses what? Read that first sentence. The encoder block uses what? Self-attention mechanism for what? To enrich each token with contextual information. That is, I am generating word embeddings, right? Each word embeddings is represented in n-dimensional vector where the context of the word would be defined, and this context of the word is being enriched using which mechanism? Self-attention mechanism. Okay. Now, the position-wide feed-forward neural network is again taken. As I told you, we have two things. In encoder, two operations. One is self-attention, other one is feed-forward. The same thing is happening. I'll explain you again in depth later. Okay. Just understand the overall diagram. So first, this is the basic diagram where I take input embeddings, I give it to encoder, generate features, give those features to decoder, apply it to softmax and take the output. Okay. Now this diagram is all about what? What is there inside the encoder? So there are two operations that happens inside the encoder. What are they? One is self-attention and the second one is feed-forward neural network. That is the reason when we were talking about transformers, I said we study about word embeddings, we study about self-attentions, and then we study about multi-layer perceptrons. So multi-layer perceptrons are nothing but your feed-forward neural networks. So what do you have inside the encoder block? Two operations are carried out inside the encoder block. What are they? Self-attention mechanism and feed-forward neural network. Okay. Now look at this. When I talk about feed-forward neural network, it has a linear layer. Again, when you say feed-forward in hidden layers, what do we have? ReLU activation functions, because ReLU takes all the input from 0 to 1 and gives you the original input, max of 0, x, the ReLU activation function, and process each embedding vector independently with identical weights. What is attention mechanism? Adding weights to what? Adding weights to what? The tokens generated. That is what is being explained here. Okay. So, each embedding vector would be processed independently with what? Identical weights. So, each embedding vector with contextual information from the multi-head attention. So, what does multi-head attention gives us? Multi-head attention takes what? Embeddings as input, contextual embeddings, and that will add some weights using attention mechanisms and generates what? And generate what? Position-wise feed-forward embeddings. Feed-forward embeddings. That would be given as input to the next layer, which is position-wise feed-forward layer. Okay. Now, after we give it to position-wise feed-forward, before I give it to feed-forward, I take adding and normalization. After feed-forward, again I have one layer which is called as what? Adding and normalizations. Okay. Now, when you look at this on the left hand side, can you see those word residual connections? Okay, now let me tell you what are these residual connections. Listen to me. I'll take a word, look at this. I'll take a sentence, I'll generate the input tokens of that. Okay, I give it to multi-head using self-attention. I give it to multi-head attention where I generate the outputs. When I take new word, all the previous word would be the same, only just that the new word is added, right? So I go for adding here. I don't want to repeat the process. See, I am ASHA is there. If suppose I say I am teaching, I want to take I am ASHA from the previous state. I don't want to read I am ASHA again. I just want to add I to this I am ASHA. And in the next step, I just want to add am to I am ASHA I. Are you getting my point? So, hence we go for adding and normalization here such that I will not repeat the process of reading each word every time again and again, because one time step we have the previous word getting stored. Okay. So, residual connections are key architectural features in transformers that will help in what? Deep learning stability, gradient flow and efficient training. Hence, I use that residual connections 2 times. When do I use that? After I perform multi-head attention, I use residual connection, that is adding and normalization. After feed-forward network also, I again use residual connection by performing what? Adding and normalization. That is, the previous output would be stored. If you have new input, I will not read word by word of the previous output. I will just read the previous output as an entire sentence and just add the new word to it. Hence, I say adding and normalizing. Are you all clear with me? Yes or no? Got it? So, this is called adding and normalization. Residual connections help us doing that. Ippudu ardhamainda what is happening inside the encoder? Now tell me what is happening inside the encoders? 2 operations. One is multi-head attention with respect to self-attention. Adding and normalization after that. Output of this is given to what? Feed-forward neural network. From where I again generate what? Adding and normalization. From there I get the features. Got it? We'll still understand in more clear way how multi-head attention works and all that. First, you understand this picture. Are you all okay with the encoder block, guys? Yes or no? Okay. Now look at this. Okay. After each residual connection, there is a layer called what? Normalization. That is, I perform multi-head attention, normalization. I perform feed-forward network and perform normalization. Okay. Like when we talk about gradient descent and all that, we have batch normalization, processing them in steps, right? Similar to that, layer normalization aims to reduce the effect of covariance shift. That is, instead of using the same words of the sentence again and again, word by word, I use the entire sentence like that. Okay. In other words, it prevents the mean and standard deviation of embedded vectors moving around, which makes training unstable and slow. Okay. Now, what is the output of the encoder? Got it? So, this is the entire encoder block architecture. Input, don't look at the slide, look at me. Input, tokens, word vectors, positional encoding, give it to encoder. Inside encoder, what is happening? Multi-head attention, that is with respect to self-attention mechanism, adding and normalization, feed-forward neural network, adding and normalization, features. Got it? Now, let's get back to decoder. What is happening inside the decoder? What is the input to the decoder? Features. Features are given to what? All the decoder blocks, not just one decoder block. Features are given to all the decoder blocks. Can you see residual connections here again? Okay. Now, in encoder, we have multi-head attention, feed forward. Similar to this, in decoder, we have 2 operations. One is called masked multi-head attention. What is it called as? Masked multi-head attention. That is, I'll mask a word and try to predict. This is predicted output kind of thing. Okay. So, decoder takes predicted output from here and takes the original output from the encoder block and process both of them together. So, we have masked multi-head attention. Along with that, I have positional wise feed forward again. Akkada only masked multi-head attention, sorry. In encoder, we have multi-head attention and feed forward. In decoder, we have what? Masked multi-head attention, features as input, and then we have feed forward neural network from where we try to generate the output. Is it clear, everybody? So, this is the block diagram of what? the decoder block. Okay. Now let's see what is masked multi-head attention. Okay. Masked multi-head attention means the multi-head attention receives the input with mask. Mask ante I hide that word. Today ASHA is dash in the auditorium. Teaching in the auditorium. I mask this word teaching and try the model to predict that particular word. This is called masked multi-head attention. Okay. Now look at this. What is this diagram? Decoder block. So what is there in the decoder block? The features are not given to multi-head attention. The features are given to where? The features are given to multi-head, but multi-head also takes what? Features along with what? Masked multi-head, which would be the prediction. Okay. So from encoder block, please understand this. From encoder block, we are taking features. Okay. Which would be given to what? Multi-head attention in the decoder. But before that, the decoder also considers what? The output from where? Masked multi-head attention. So the decoder will take positional encoding word embeddings, masked multi-head, adding and normalizing. Along with this, it also considers features, residual connection again. After that, we have the same process again. Positional feed-forward neural network from where we generate the outputs. Are you all clear with this? Yes or no? So decoder block consists of three things now. What are they? Masked multi-head attention, which is the prediction probability. The output of the encoder features are given to multi-head attention, from where we give it to what? Positional, feed-forward, positional encodings. Okay. Now this is your transformer architecture put together. Is that clear, everybody? Yes or no? Encoder block, decoder block with all residual connections, with all features, inputs, outputs, linear layer added, softmax added, and the output probability together. Are you all clear with the architecture of transformer? Any doubt in this? We will understand it more clearly again. Step by step, I'll take an input example and we'll understand it. Just understand the architecture. What is there at every step, you have to understand. Got it? Yes or no? Okay, we'll proceed. Okay? What is the difference between this diagram and this diagram? I am again depicting that multi-head attention very clearly. When I talk about multi-head attention, I am introducing what? I take the word embeddings and introduce query key value, QKV values, calculate scale dot product of that and generate what? Multi-head attention score. That is what I have represented here. Look at that. I am taking input. I am generating word embeddings. I am adding positional embedding to that. I am performing self-attention, that is QKV. From that I am generating what? Residual connections with which I generate features. The features of this encoder block would be given to what? The decoder block, where I again have multi-head attention. Along with multi-head attention, at the bottom I have masked multi-head attention. See, can you see on the right hand side, I have first QKV values in the bottom, that is masked multi-head attention, masked normal multi-head attention, and then I give it to linear layer, softmax layer and try to predict the probability. This diagram is same as this, but what is the difference? I am just representing the attention QKV values here in the diagram. So you find different types of diagrams on different books, different pages. They have their own depiction, like they represent with QKV, or few people give you two blocks, self-attention and then feed-forward. Okay, something like that. Both are one and the same. Okay, now let's consider this example. Okay, now I have a sentence that is called prompt, that is the input. Okay, now transformer takes this inputs and generates the output. Let's read what is the prompt here in the sentence. What is the prompt here? Write an email apologizing to Sarah for the tragic gardening mishap. Explain how it happened. So here I am giving what? A sentence, which I am calling it as prompt. I am giving it to the transformer model and asking it to generate what? A email. Okay. So what is the output here? It says, Dear Sarah. What are the output tokens which are generated here for the decoder? Dear Sarah, it is analyzing the content that you have given in the input. The encoder-decoder will understand the contents and start generating the outputs. So, is there any word called dear in the prompt? But it has taken a new word, dear Sarah, and it tries to generate. Okay, how does that do? How does that do? It takes the word and generates one token at a time. The decoder generates what? One token at a time, understanding the context of the words that are given in the encoder and decoder block which are processed. Okay, now look at this. So, what is the difference between this diagram and this diagram? Multiple encoder blocks. One encoder block will generate dear. What does second encoder block do? Take that dear as input, read the sentence again and generate what? Sarah. Now what would be my output? Dear Sarah. So in this way, the concatenation of the blocks inside the encoder happens. Each word would be generated in the decoder. Okay. Now look at that. Okay. So what are the two things that is happening? First, we tokenize the words, give them to stack of transformer blocks, that is encoder blocks, which are actually performed by using what? LM head. What is LM head? Large language model head. That is self-attention mechanism being applied. Okay. So I take the text, generate the text into word embeddings. This is what happening in the first tokenizer block, and then that would be given to the stack of transformer blocks from where we generate the output. Okay. So at the output, what am I taking? This is the output of decoder, not encoder. Okay. So I take the probability. So I have so many words. Let's say 50,000 token IDs are generated. I have different words. So what is the probability of the first word here? Dear has 40% probability. So what is the output token that is generated at the first level when I take that input sentence? Dear. Okay. What is the second word? Sarah. So for Sarah also, the second layer of the encoder will process all the words. The decoder will generate the probabilities where Sarah will have the highest probability. Hence, the first time step, dear had the highest probability. In the second time step, Sarah has the highest probability. So the sentence generated in the output is what? Dear Sarah. Okay. So in this way, the transformer will take the prompt as input, process that input in encoder and decoder blocks, and generates the output based on the probabilities. Okay. What is this now? So when you talk about drawbacks of RNN, each word is given what? Sequentially. One word at a time. Yes or no? First I pass I. Next I pass am. Next I pass Asha. First I pass I. Next I pass am, where I is concatenated with am. I am, like this. But here as you observe, what is happening? All the input word tokens are processed what? Parallelly inside the stack of transformer blocks. Are you observing? Yes or no? Those arrow marks, what is those arrow marks? Arrow marks are nothing but the word embeddings are processed parallelly. Okay? But look at that. At the end, what is the difference between this diagram and this diagram? Observe it clearly and tell me. Yes, very good. So I am processing all the inputs parallelly here. I am processing all the inputs parallelly here. But what is the output there? The last word, that is the depicted word that I am choosing. Is that clear? The same thing. Okay. Now, inside that, actually this is not represented in the original transformer paper. When I talk about the transformer or layered encoder blocks, we have this cache calculation. Okay. That is, as parallel processing is happening. What do you mean by parallel processing? How does this parallel processing happens? In case of RNN, I am, this will become I am Asha. Now this will become I am Asha. This is RNN. In attention or in transformers, what is happening? I am Asha. Everything is processed at a time. Okay. Next time, suppose I have I am Asha, I am teaching. All of them would be processed at a time. First, I am Asha. Next sentence, when I comes, this previous is already stored. This I would be added to that. That is, for example, I will not confuse. Let's say I have 10 words. When 11th word comes, what will I do? Will I generate these 10 words again and add the 11th word to it? Or will I take these 10 words together and add 11th word to it? This is called cached calculation. Is it clear? So inside the attention block, this happens. Okay. Now this is again the transformer LLM. What do you see in this? Same. The tokenizer is happening. Word embeddings are generated. That would be given to one transformer block in which we have again multiple transformers, encoders, multiple layer of encoders, multiple layers of decoders. Then that would be given to output vectors from where we generate the LM heads. Okay. Now look at that transformer block. What are the two important operations as I told you? Inside the encoder, what are the two important operations? Multi-head attention and feed forward. Multi-head attention is what? The self-attention. Can you see that? So inside transformer block, what is happening in the encoder? Self-attention and feed forward neural network. Got it? Okay. Now let's see one example. Let's see how embeddings are calculated, what are positional embeddings, what are word embeddings, how are they calculated, and so on with nice example. Okay. For those guys who didn't listen anything since morning, at least you see this example, you'll understand something. Ivi kuda raledante, it's of no use that you sit here. Okay. Now let's see this. I have taken a data set here. So step 1, I am defining a data set. What is the data set that I have taken, guys? How many sentences? 3. What are they? I drink and I know things. Second sentence. When you play the Game of Thrones, you win or you die. The true enemy won't wait out the storm. He brings the storm. These are the 3 sentences. What do you mean by corpus? See, data set and jusam. What is data set? Collection of data. In NLP, when you process text, that collection of text data is usually referred to as corpus. Okay? Got it? So I am taking a data with how many sentences here? 3 sentences, right? First, I'll find the vocabulary size. What do you mean by vocabulary size? The number of unique tokens, because I don't want the to be repeated n number of times, because it is waste of time processing. See, here I have only taken 3 sentences where the repetition might be very less. But if I take 1 million words, how many times the would be repeated, how many times of would be repeated in that? N number of times. There is no point in generating word embeddings for the n number of times. Hence, after we take the data set, what is our first step? We calculate what? The vocabulary size of that. Okay. So, N. So, we found that the vocabulary size is what? 23. What do you mean by 23? There are 23 unique tokens. 23 unique tokens. What are unique tokens? Without repetition. The words which have occurred without repetitions. Okay. After that, what happens? Encoding would be done. That is, a unique number will be assigned to each word. So, I have the first unique word what? I, drink, things, know, when, won't, play. So, each and every word has been assigned with what? One position. With what? One position. This is positional encoding. Okay. Now, calculating embeddings. What is step 1? In the transformer architecture, take the input sentence. So, here out of those 3 sentences, I want to process 1 sentence. What is that 1 sentence? When you play Game of Thrones, I want to process this sentence. What is that? When you play Game of Thrones. So, I'll first give the positions of that. So, what is the position of when? 5. What is the position of you? Where is you there? 17. Where is play? 7. Where is game? 12. Off is in 15th position. Thrones is in 19th position. Now, what is the input sentence here? When you play Game of Thrones. Please understand this. What is my input sentence? When you play Game of Thrones. So, what did I do first? I already have generated unique words. For each unique word, I have generated positions. Now, for the input word that I take, I am taking the positional encodings. Okay. Now, after this, for each For each token, I have to take a n-dimensional vector space. In the paper, attention is all you need. What is the size of n-dimensional vector? 512. 512 తీసుకుంటే ఇక్కడే ఉంటాం ఇంకా ఇది ఒక్కటికే ఓన్లీ వర్డ్ ఎంబెడింగ్ క్యాలిక్యులేషన్ అయిపోతుంది ఎన్కోడర్ డీకోడర్ విల్ నాట్ బి ఏబుల్ టు డూ సో ఫర్ ఆర్ ఈజీ అండర్స్టాండింగ్ లెట్స్ put 512 aside. What do you mean by 512 embeddings? The word when will have 512 depictions. The word you will have 512 depictions. The word play will have 512 depictions. I don't want this. I don't want 512 as of now. So let's take some 6. Okay. So each word has 6 layered embedded dimensional vector. So what is the sentence there? When you play Game of Thrones. So I have position to each of them. I also generated what? 6-dimensional embedding vector for each word. I have generated what? 6-dimensional embedding vector for each word. Ardhamaitunda leda? Okay. So what is that first table? Positions of the words. What is the second table? Vector, n-dimensional vector space of the words. Okay. So this is what we are doing here in the step 1. We take the input, generate the embeddings, concatenate the embeddings with what? Positions. Did I concatenate them? Not yet. I have generated positions, I have generated what? Word embeddings. So what do I do now? In the architecture I have to concatenate. Okay. So when you are calculating the position encodings, we go with these two formulas. For even value, for odd value, we have these two formulas. Okay, please note down these formulas. That will help out in coding. Okay, for even position, we write the embedding as sign of position by 1000 2i by d model. What is this d model? Dimensional model. What is the dimensional vector that I have taken here? 6. Okay. For odd position, it is cos. For even position, it is sine. How does sine wave look like? Sine and cos, you know about it, right? Yes. Odd and even position, sine and cos. The basic understanding. Okay, now look at this. Yes. I am calculating position encodings here for even and odd position vectors. Yes.
You told we are calculating what positional embedding so that we will get unique set of words.
Yes.
However,
What? Unique words are before positional encoding. Unique words are generated because you want to reduce the pre-processing. Positions, because each and every word should have position for sequential order processing, right? Yes. Where each word, what is the position of each word? Okay. Done with this? Done with this? Okay, let's quickly recap first 5 steps. What did we do in step 1? Read the heading. What did we do in step 1? Define what? What did we do in step 2? We have found the vocabulary size. What did we do in step 3? We have encoded. Step 4? Calculated the positions for the given input sentence. Okay? In step 4, along with the positions, I am also generating what? Embedding vectors for each word, n-dimensional embedding vector space. Okay? I am calculating what? Positional embeddings. Okay? This is how. What is d dimension? 6 dimensional vector size that I have taken. What is the position here? 0, because this is for when word. Are you observing? Look at this. First, I have how many words? 1, 2, 3, 4, 5, 6. When you play Game of Thrones. First, I will take only one word. I will take only one word, which is what? When. For this when word, I am calculating positions. Okay. I have even, right? What is even? What is even? The word embedding of the word when. What is E2? Word embedding of the second word. What is E3? Word embedding of. So we have to calculate the positional embedding for each words, right? So first I'll go with one word. What is the first word? When. So what are the values for when? 0.79, 0.6, 0.96, 0.64, 0.97, 0.2. I take that. In E1 I take that. I calculate the position. First is even, odd, even, odd, even, odd. These are the positions. Based on the position, I'll apply the formula and calculate P1. That is the positions. Is that clear, everybody? Yes or no? Okay. Similar. What is this table now? P1, P2, P3, P4, P5, P6 of all the words. How would I generate P1, P2, P3, P4, P5, P6? Like this. Okay. Now this is what that step is all about. Generating what? Positional encodings. Now what do I do in my next step? I have to concatenate what? Or I have to add what? Word embeddings and position. How are word embeddings represented? E1, E2, E3, E4, E5, E6. How are positional embeddings represented as P1, P2, P3, P4, P5, P6. Now they are concatenated and generated as EP1, EP2, EP3, EP4, EP5, EP6. Is that clear, everybody? So this is step 1. Before we give it to what? Multiple layered encoder block. Did you all understand till this? Yes or no? So what did I do here? Take a data, input data, generate the unique words out of it, give the numberings for that unique words, generate the positions for the input sentence, calculate the positions of the input embeddings, generate the word embeddings, concatenate them and generate EP1. What is E? Word embeddings. What is P? Positions. What is EP1? Concatenation of embedding and positions. Okay. So the resultant matrix from both combining matrices. What are both combining matrices? Word embedding and positional embeddings will be considered as input to what? Encoder part. Is that clear, everybody? So we have 3 days, right? 2 more days for your session theory. So in one session, we'll discuss encoding along with the coding. How does encoding happens along with coding. Third day, decoding with the coding, and we'll end off transformers. Is this clear, everybody? Yes or no? So far we have seen only how inputs are given to the encoder. Tomorrow we will see what? How those inputs are processed in the encoder blocks with 2 important blocks inside encoder. What are they? Multi-head attention and feedforward. Okay.